So I do expect you to go through and do the homework, the rest of the homework for Chapter 2, if you didn't finish it, on heat and temperature. Based on grading the notebooks, it looks like most people already did that. That's fine, not a big deal. But that does need to show up in your homework book. Okay? So, temperature. Temperature and heat are kind of an odd system or an odd thing to talk about because we don't really have a way to grab a hold of temperature or heat. We know that we feel hot or we feel cold, but what do we have physically to hold on to? And that we don't really have. So that makes it a little more difficult to consider. When we're looking at temperature, the way your textbook describes it, which I think is a pretty good way to do it, is looking at the average kinetic energy for an individual sample. Okay, so we'll take any sample and we're approximating its average energy. And we're making that average energy our temperature value. Okay? It's a little bit of an odd comparison because when we look at energy units, we don't see temperature as an energy unit. So it's not really energy. It's just a way to monitor that energy as best we can. So it's kind of odd. Turns out we end up with 3 different scales for our temperatures or reporting temperatures. In the US, for some reason, we've stuck with the Fahrenheit scale. I don't know anything on the history of that, but there's probably, again, some old dead guy to blame for that and why we're still using it. Then we've got Celsius, which is typically used by the rest of the world, and it does show up in science occasionally, and it depends on what field you're looking at for when that degree Celsius shows up. Typically, the older the field, the more likely you see the archaic use of Celsius or Fahrenheit. The last one is Kelvin. Kelvin is our absolute scale, and it's most widely used within science. It's just the easiest to work with just because what we'll see here in a second. Okay? So the reason being is we can go through and now look at some common temperatures to evaluate. One of the more common substances to evaluate would be water. Why would we pick water as a substance to compare our temperature scales on? There's 2 big reasons. Number one, how much of our planet, or roughly 70–80% of our planet, is made up of water. It's a very common solvent, very common substance, very easily accessible. Next big reason that I would kind of lean towards, how easy is it to find the liquid, the solid, and the gas? Okay, very easily done. We can both decrease the temperature by going to colder altitudes to see solid water, and we can add heat to it to get it up into the gas phase. So we get a substance that allows us to see 3 different phases, all within a relatively tight temperature range, and that's why we came up with a lot of these scales. Okay? When we look at Fahrenheit, okay, the numbers are up here, and you'll notice that those dashes look awfully a lot like minus signs. They are not minus signs. Just want to clarify that those are colons. Okay, how many of you knew the freezing point for water in Fahrenheit? A couple hands. How many people knew the boiling point of water in Fahrenheit? A few less. Why do we not know the boiling point in Fahrenheit?
Because it's weird.
Oh, it seems weird. That's a reasonable guess. 212 degrees Fahrenheit. Okay, so let's think to Celsius now, though. So we grew up in the U.S. Well, most of us probably grew up in the U.S. with the Fahrenheit scale. What's the freezing point in Celsius?
0.
Wow, an awful lot of you seem to know that answer. What's the boiling point? 100. Very, very odd to me. I don't quite understand this. We grew up with Fahrenheit, and yet we don't know our most common temperature ranges within the scale that we use. But we know the temperature ranges in a scale that we don't commonly use. I still can't quite explain that. It doesn't mesh with anything in my head. Okay? But those are our 2 standard ranges. Okay? With both of these scales, there's an interesting dilemma. Can I get colder than 32 degrees Fahrenheit?
Yes.
Yeah. Can I get so cold I go negative Fahrenheit?
Yes.
How about degrees Celsius? Yes. Okay, what's the problem with that? When we go through and do any kind of mathematics, we said we're afraid of a lot of things. Exponents, powers of 10. One of the other big ones that we were afraid of, which works out well with this problem, is what? The negative symbol. That negative symbol tends to mess with our heads. It confuses us. It's the opposite of what's supposed to be there. Opposites are always difficult. Why do we not like the Fahrenheit and Celsius scale when we're dealing with science? Because it introduces a negative symbol or negative sign. That messes with our mathematics. So someone went through and said, there's got to be a better way to do this. That happened to be Kelvin. And with his temperature scale, again, we're looking at colons. That dash is really bugging me. Okay. We can look at the freezing point of water being 273 Kelvin. By the way, not degree Kelvin. Learned that this morning too. Okay. And our boiling point is 373 Kelvin. Both those values are positive, which is kind of nice. Can I get less than 273 Kelvin? Yeah. But what's the sign on that number? Still positive. Can I get so low that I go negative Kelvin? Officially, no. Leave it to a scientist or a physicist to go through and actually prove we can get negative Kelvins. We can, trust me. Seen the science. We just can't go through zero. Okay. Very, very special conditions to get those negative Kelvins. Okay. Very, very unlikely situation. But they were able to mathematically and experimentally prove that. As far as we are concerned, Kelvin is always greater than 0, which means it is always a positive value, which means we don't have to worry about this, where did it go, stupid negative symbol getting in the way and messing with our calculations. Okay? That's one of the reasons why we tend to stick with the Kelvin scale. It simplifies the mathematics, and in most circumstances that we would deal with, it's like 99.999999% of the time, it is a positive value. Okay? So kind of neat. So that's one of the reasons we'll use the Kelvin. Of course, since we've come up with different units for each of these, what do we also need to know? We need to be able to convert between them. Okay? This is where there's all sorts of massive typos on the slides if you're looking at the next slide. Okay? So the first thing we would try and do is compare these, see if we can figure out some simple relationships. If we take a look at degrees Celsius and Kelvin, it's the relationship between our freezing point. What's our difference? 273. Well, what's our difference? 273. Oh, that's nice. They're just different by 273. Ow, right in the ear. The other option is we can now shift to Fahrenheit and Celsius. We could go through again with our freezing point. What's that difference look like? 32. Let's move to the boiling point. That difference is not 32. Okay? One of the big reasons why we can't convert between Fahrenheit and Celsius very easily is because it's not an easy relationship. The Celsius to Kelvins shift is a relatively easy conversion, but our Fahrenheit and Celsius one usually gets bungled and confused by people of lesser brains like myself that can't ever get them right. Okay? So, like I said, be careful. There are some pretty big typos on this. We'll take a look at first the degree Celsius to Kelvin. That is our correct conversion. If you are given the degrees Celsius, you can add 273.15 if you want to get super accurate, and you now have your Kelvin value. If you wanted to do the reverse, if you have Kelvin but you want to get degrees Celsius, what do you need to do? Subtract. So we could start with our Kelvin and now minus 273.15. Why the 0.15? Well, that's what it is. Why did I write 1.5 or 0.15? Because I happen to remember it. That's all it is. Okay? The standard conversion that you're responsible for is the 273. I do expect you to remember this one. Okay? The 273, you don't need to remember the 0.15. But now that I've said 0.15 a couple times, hopefully you'll remember that anyway. Okay? So that's our conversion between degrees Celsius and Kelvin. Nice and simple. What happens when we move up to Fahrenheit and Celsius. Well, really, in my opinion, now all hell breaks loose. Okay, you get all sorts of fractions. There's even a freaking negative sign showing up in there. It's just a mess. Okay, does anybody happen to know where the mistake is?
5 over 9.
5 over 9 where?
Where there's the 9 over 5.
Which one? There's 2 of them. One of them is correct. This is why I hate this stupid conversion. I never remember which one it is, 5 over 9 or 9 over 5. Our Fahrenheit to Celsius is 5 over 9. Okay? What? It's fixed or not?
So what was that 5 over 9 again?
The 5 over 9 is happening with that middle equation when we're trying to convert Fahrenheit into degrees Celsius. We have to go through and use that formula. We would take our degrees Fahrenheit minus 32, take that quantity, multiply it by 5, divide by 9, and we now have our degrees Celsius. Okay. Most of you are taking the lab here, right? What's the formula given in lab? Is it 5 over 9 or 9 over 5? No, what was it? Yeah. 180 over 100. I'm not going to get into how we can derive these formulas because I don't like them to begin with. Why 180 over 100 in the lab? What is 180 divided by 100, by the way?
1.8.
What is 9 divided by 5? 1.8. So it is the same number. Why did they show 180 over 100 and not 9 over 5? What was the difference between our Celsius and Fahrenheit at freezing? 32. What's 180 plus 32? 212. What was our boiling point? 212. There's where our 180 is coming from. All right. That relationship is embedded in there. If you know the freezing point and boiling point of those substances, you can derive a formula that's going to get you to this exact same situation on determining that conversion. Okay? Like I said, I don't want to derive it because I think it's pointless. Crap. Should have covered the mic. So these formulas, as you can tell already, I have such a high opinion of. So what do you think about an exam? Am I going to have you memorize these? No, I will give you these on an exam. You still have to be able to use them, but I'll give you these formulas. Okay? Questions about that? Okay. Let's take a look at an example and real quickly fix this. Looking at 5 over 9. Okay, we're going to start with body temperature, 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius? What is it in Kelvin? Okay, we should set this up like we set up all other problems. Where do we want to end? Whoa. We want to end in degrees Celsius. Which of our two equations gets us degrees Celsius? Red or blue? Red. We'll start with what we're given, our 98.6 degrees Fahrenheit minus 32, and then we'll multiply by our 5 over 9. Okay. Those of you that have pushed some serious mathematics, or maybe some not so serious mathematics, might be cringing at the way I've got that written. Okay, what's the problem with how I've got that written? You enter that into the calculator. Take 98.6 minus 32 times 5 divided by 9. You're not going to get the right answer. Okay? Has to do with the order of operations of your calculator. It will do the multiplication and division first, then do your addition and subtraction. So your calculator thinks that you want to do this calculation. Not true. You want to do your subtraction first, then your multiplication and division. Very simple mistake. Easy ways to get around it. Include the parentheses every time you do your calculations. As our calculations get longer and longer, you may start to get really sick of parentheses and have to count way too many of them out to make sure you got it set up right. But at very least, you're setting up your orders of operations correctly. You don't have to worry about that mistake. Anybody happen to know what your answer comes out to? That answer shows up as a multiple choice answer on your exam. Are you correct? No. Why'd you get the problem wrong?
3 sig figs.
Have to evaluate your sig figs. 5/9, those are our exact numbers. Okay, we could even come back from where they came from. We're looking at the 100 and the 180 with our 3 sig figs. And we've got the 32. Okay, we'll leave that as infinite or 3. What about the 32? I only see 2 sig figs. Okay, the 32, and it's ultimately actually our 5/9 as well, are also a bit tricky. At minimum, they have 3 sig figs. How do we know that? You're converting between systems, metric to Fahrenheit, or sorry, metric to English or English to metric. That conversion is always 3 sig figs. Okay? We can then go to the actual number we were given, which was 3 sig figs, which means our answer is actually 37.0 degrees Celsius. Okay? Questions about that? How do we convert it to Kelvin? Is there a question there? Thinking about it?
Yeah, like, I'm kind of confused.
Yep. Go ahead.
Like, how did you end up from 37 to 37.0?
So your calculator will tell you what the number is, and presumably the calculator gave you exactly 37. Was I wrong? It gives you exactly 37. That's only 2 sig figs.
Oh, okay.
You have to interpret what the rest of the problem gave you. The rest of your problem says 3 sig figs. That is 3. Okay? So you have to make sure that you get that third significant digit in your answer. Okay? But we can't change the value. So what do we have to do? Put a 0. And we'll also have to include the decimal point, otherwise we jumped up to 370 degrees Celsius, and that's a pretty hot body temperature. I thought it was funny. Okay? How do we convert to Kelvin? We can add our 273.15 to that number because I told you only have to memorize the 273. Our answer comes out at, that's a 310. We carry all our numbers down, 0. Kelvin, how many sig figs are we allowed to carry? 3. Our answer, 310 Kelvin. Get rid of the last 0. Why? Least accurate measurement. Our least accurate measurement is the 273. It doesn't have that extra decimal place. Okay? Yes, hand.
What if you put the 272.15?
If you add the 0.15, you're now increasing the accuracy. So if we did it with the 0.15, let's go through and do that math. Here. 310.15. What's our least accurate decimal place? Our tenths place.
So just be like 310.2.
So 310 point, why did you say 0.2? You're right.
For sig figs.
We go to
Oh, and you round it.
our least insignificant, or sorry, our first insignificant number, which happens to be 5. So we round up, and our final answer would be 310.2 Kelvin. Okay? Questions about that? Oh, yep.
So you don't have to put the 0.15?
You do not have to put the 0.15. On the exams, I will make sure that that is accounted for in your multiple choice answers. That I don't give you both 310.2 and 310, because that would be really mean. Okay, other questions? Okay. Next part of this is what's going on with heat. So our heat concept is slightly different than temperature. Okay? They're both measuring a heat energy, but again, they're different. What is the difference? Our temperature was the average energy. Heat happens to be the total energy. Okay, why does that matter? The best way to think about this is take a look at these two beakers. One has 500 mils of water, the other one has 1,000. Okay? They're both at 100 degrees Celsius. If you have to choose which one gets splashed on you, you probably pick the one with the least amount, because that's less heat that can be transferred into your body, right? Even though they both have the same temperature. There's less possibility or less burns in one case than in the other. Okay? So heat takes into account our total energy, which also has to take into account the volume, or not the volume, but the mass, the amount of that substance at that temperature. There's two ways that we can represent heat. Typically see it in joules or calories. A lot of that depends on what kind of context you're working with. I personally prefer heat in joules because in the context that I've had to work through in my experiences, tend to deal with joules. Why would we use calories instead? We talk about nutrition or food. Those are reported in calories. Interesting question. They are reported as, whoops, come back here. They are reported as this calorie. Is that the same as the calories for heat? What's the difference between those two?
That's kilocalorie.
That ends up being what the answer is, but what's the difference between calorie in bold and calorie that I wrote? Go ahead. Capital C. Okay, that is your difference. Capital C, calorie, is a food calorie, and in that case it represents 1,000 lowercase c calories. Okay? So when you're looking at nutrition, you're still looking at an energy, but they've changed how you interpret it, and that's again going back to that science or that field. Most people worked with it as the 1,000-fold because it didn't make sense to look at it in the other way, because you'd have a whole bunch of zeros you'd have to write at the end of it. Okay? So it's just a perspective on it. Unfortunately, they both look very, very similar. Okay? Our capital C calorie is different than our lowercase c calorie. So just kind of be aware of that. Your textbook will probably throw questions at you like that. I won't. Okay? So just be cognizant. That's all I'm actually asking in this case. So what can we do with the heat? Well, individual species, or each compound that we could look at, or each element or material, is going to have something known as the specific heat. And what that's a measure of is the amount of heat required to raise the temperature, or raise 1 gram of that material by a single degree Celsius. Okay, so it's just looking at how much heat that compound or that species can absorb energy. And that's where we get our specific heat, and we get some new units showing up with this, because it's going to relate our energy to grams and degrees Celsius. So one thing that we get out of this is a conversion factor. I can now relate energy to mass and temperature. Okay, so that's a fun little relationship that we will probably evaluate later in the semester. We also see another relationship up here. I mentioned that we had calories and joules as our potential units for energy. What is the conversion factor between calories and joules? One calorie happens to be 4.186 joules. How did we just solve that? What happens if we multiply both sides of this equation by grams? Anybody?
1 calorie.
Grams cancel, right? What happens if I multiply both sides by degrees Celsius? Degrees Celsius cancels. What am I left with? 1 calorie equals 4.186 joules. Okay. I believe our 1 calorie per gram degree Celsius is based on water, because I'm pretty sure that 4.186 that I remember is coming from water as the definitive species for measuring this. Okay. The next part of this, we could go through and use it as a conversion factor. We probably won't end up doing that until much later in the semester. So we need to come up with some way to ask questions about it now. And even further, it would be nice if we could ask a question that involved not using mathematics, okay, or not having you write out some long calculation. So what we could come up with is looking at what that number means. The larger the specific heat, that means the more heat is required to be added to the species to raise the temperature. Okay, well, what does that mean as far as conductivity? If it's a really big number, is that material, or is the material that has that specific heat, a conductor or an insulator from heat? Okay, way to think about it, you put your hand to that material. Okay, your hand is going to be a measure of that heat. When is your hand going to get burnt? When the material gets really hot. How do we measure the material getting hot? Temperature has to be elevated. If I put in 1,000 joules of energy and the temperature only goes up by 1 degree Celsius, do I burn my hand? No. The bigger the number, the better insulator the material. The smaller the number, the less energy we put into it, and our temperature skyrockets. Okay? How could we take advantage of this, say, in cooking? What material do we want to use when we pick our pots? We pick a metal. Why do we pick metals? What's a property of our metals? That's true, but why does it get hotter faster? Metals are conductors of heat, which means their specific heat is very, very low. What's the best, this may go out to all the cooks out there potentially. What's the best metal to use for a pot? Copper. Copper is one of the most expensive sources for your general pots. Why? Well, first off, it's expensive metal. Okay. But then we like to use copper because it translates the heat from your stovetop throughout the entire pot virtually instantly. That means when you cook in a copper pot, there's no hot spots within it. Everything is the exact same temperature around the entire pan. Okay? And that's because its specific heat is relatively low. Okay? So kind of a neat process. So let's think of an idea now for an exam question that could cover all of these bases. Which of the following substances is expected to have the largest specific heat? Hey, we can actually use this to discuss how we should answer exams or answer questions on the exam, particularly multiple choice. So right off the bat, I heard a couple people shout out answers. I would argue that is a very bad approach to this. Okay? Not because shouting out the answers is a bad idea, but okay, you're participating. That's a good thing. What you should start to do is put down information, translate what the problem says. If we have a large specific heat, what does that mean? Is it a conductor or an insulator? It's an insulator. Spell that right? I think that's right. Okay. We can now get a quick glance at our possible answers, and we see a whole bunch of different elements. Okay, so we could panic and say, okay, well, before we look too much at that, let's look at our periodic table. Okay? What species are insulators? Okay, so an insulator means it is a poor conductor of heat. Looking only at the periodic table, or thinking back to that section when we talked about periodic trends, particularly of the different materials within it, what species are poor conductors of heat? The nonmetals. So we would now say that when we go to look at our answer needs to be something that is where on the periodic table? The upper right corner. Because in the lower left corner, we are looking at metals. Metals are conductors of heat. We want something that is an insulator. Okay? So we could now go through and take a look at our possible answers. Where does Ca show up? Left side, what does Ca stand for? Calcium. Where does Cr show up? Okay, we should address that whole left-right thing. Where's our left versus our right on a periodic table?
Anything less than the zigzag.
We're looking at our zigzag. Okay, remember that's where our metalloids were. Non-metals were above that, metals below that. Okay, where's chromium? Sorry, Cr on the left, which happens to be which element? Chromium. Copper. Okay, we could do a couple things on that. We go, oh yeah, I remember him talking about copper being a great conductor of heat. Or, what's our symbol for copper? Cu. We find Cu. Still on the left-hand side. Pb. Where's Pb? Left-hand side again. It also happens to be known as lead. Carbon. Where does carbon show up? On the right-hand side with what symbol? C. Capital C for carbon, not calorie. Okay. So between those options, we went through and specified that this guy is a metal, 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 non-metal. One more piece of information we could write next to our insulator. It needs to be a non-metal. What's our answer? Carbon. Okay. We minimize the amount that we have to think in our head by writing that information down. Okay? That requires time, but again, it goes back to something that we've talked about before. If you spend the time and get the answer right versus spending no time and getting the answer wrong, if you get the answer wrong, you fail the class. You get the answer right, you're doing at least a step above failing the class. Okay? So spend the time, get as much information down on your exam as possible so that you can then try and go back through and solve. Okay? So simple little notes to yourself. Make sense? Questions about specific heat? Oakley dokley. Artichokely. Chapter 4. We're going to move into chapter 4 now. The homework is posted as an announcement. We've made it a new announcement, so it should show up right at the top. All of these questions have been listed up there. So like I said, we're going to, what's that?
Is it on Canvas?
It's on Canvas, yeah, under the announcements. It is not in the slides that are posted currently. I did this morning. So we're going to look at chapter 4. That's probably all we're going to get to today, is looking at some of the history behind these and getting some understanding of atomic mass and atomic numbers. Then we're going to shift to chapter 5, look at some simple periodic trends. And then we're going to go back to chapter 4 and look at everybody's favorite quantum mechanics, which is a joke, by the way. Quantum mechanics are never anybody's favorite. And then we'll move back into chapter 5, the nanospace. Okay? Questions about any of that? Okay. So Dalton starts off our early atomic theory. We're looking at the early 1800s. Okay, right around that turn of that century. I think we're looking at 1805 to 1811, something like that. Okay, Dalton went through and he came up with some postulates or theories behind atomic structure and how we build things. So the first thing he went through and did was said that we had elements. Those elements were composed of tiny little particles, and he called those atoms. Okay? One of the big things that he said about atoms is that they were indestructible. You could not take them smaller than an atom. Okay, remember, this is early 1800s. That's a pretty big leap to come up and say, hey, well, I've got a single particle. Is that theory true? No, because we have subatomic particles, protons, neutrons, electrons, which we'll also talk about today. Okay, but remember, this was his initial approach. The next part is all atoms of an element are identical and have the exact same properties. Okay, also an interesting idea. Is it true? No. What's an example that we could go back to that we've already talked about? Sodium metal. Okay, we can make it even more exciting. Let's use potassium metal. Potassium metal, when it's thrown into water, does what? Boom! We get all sorts of energy released, highly reactive, very dangerous, not particularly fun. Okay, if we ate a bit of sodium metal, potassium metal, that would be highly unpleasant. Okay. However, anybody in biology know something about how muscles work? What do we need? Potassium and sodium ion. But we just said if we eat potassium, we go kaboom. Why do we not go kaboom? It's potassium ion, not potassium element. Okay? So the potassium atom, that nucleus, or that piece, rather, can have different properties. We can change it. Why did he not realize that? Because he didn't have an understanding that there were smaller pieces than the individual elements. As soon as we break it into smaller pieces, now we can get different properties. Okay? Other theories. Atoms of different elements can combine to form compounds. So that's a nice simple thing. We can take it to multiple different pieces, put them together, and we got a new thing. Okay? He then also went through and said that those pieces combine in whole number ratios. Okay? Which also seems like an odd statement, but it's actually a pretty big one. Remember, we can't see atoms. So let's scale an atom up to something a little more reasonable to deal with. Let's say a bicycle tire. If I give you 2 bicycle tires in a bicycle frame, how many bikes can you make? How about I give you 2.5 bicycle tires? Still just 1. What's that extra half a tire doing? Right? That doesn't even make sense to have half a tire. So what we're looking at is these numbers of things are coming together to build larger structures. We're not looking at dividing them into smaller pieces. We're taking a single unit, and that's what's being used to build. Okay? Next thing he said is that we can then combine these in different ratios and differing amounts to get a different compound. Okay, so it's kind of a fun thing to play around with. Good example I just happened to think of. Anybody know the formula for water? Anybody know the formula for hydrogen peroxide? H2O2. Exact same elements used in both. Anybody know what happens if you drink hydrogen peroxide? You don't want to do that. Okay? Water is something that we need to survive. Hydrogen peroxide is not. Hydrogen peroxide is an extremely dangerous species to be ingesting. Okay? Which is why we use it to clean wounds, because what's happening when it cleans the wounds? It kills everything it touches. Okay? So not a pleasant thing to have. We're using the exact same elements to make it up. We're just changing the ratios. And it changes the properties of that new compound. Okay? So what we can see on the right-hand side is that we've got my little star. That could be our compound, and we could decompose that into the individual species that made it up. So it was made up of a circle and some triangles. Okay? We could then rearrange those triangles with something else and get a new compound that wouldn't be our sun or something like that. What's the next image? Any ideas what that thing is? Okay, as a pseudo hint, this top section is actually already in the class. That's Dalton's periodic table. So instead of using symbols, letters that we've adopted, he's gone through and drawn circles with lines and dots and squares and triangles. And it looks like a snowflake in there too. Maybe a Phillips size 2 head. Okay. Can you imagine looking at our periodic table with 118 elements on it, as a bunch of circles and stars and squares? Okay. Not particularly fun to imagine. But when you're only working with, 20 different things up there, it's not that bad. Okay. It's still a bit mind-boggling, in my opinion, to go ahead and put it together like that. What are the next sequence underneath? Those are the compounds that he was able to discover and the relative ratios of each of those individual species. Right? So what he did was he was able in the early 1800s to go through and take something that he could not see and actually build it and come up with a physical representation accurately depicting what was occurring. Kind of mind-boggling, the amount of information that he was actually able to pull out of this and how much of that was actually relatively correct. Okay, so kind of neat. Now we shift to 100 years later, and we can look at Thomson. Okay, Thomson was able to build an experiment. That looks like we jumped a little bit.
Yeah, we did.
Oh, no, never mind. Sorry, just remember what was going on. Thomson was able to come through, and he discovered 2 subatomic particles. Forgot, this was one I didn't start with the experiment, started with the result. He found electrons and protons, or something rather negatively charged and positively charged. The only thing he was really able to determine was that one was negative and the other one was equally positive. Could not associate a number with either of those. He just had their relative positions of each other. Okay? This was a pretty phenomenal discovery. After 100 years of doing research and looking at all atomic particles, he was able to find out that atoms were made up of smaller pieces. Okay, so that's kind of a neat observation. We don't have just a single atom. Bromine isn't just bromine. Bromine is composed of the pieces of electrons and protons. Okay, so these are our subatomic particles that go through to build this. The next part is what I find the most fascinating. How was he able to discover this? It really hinged on the discovery of one thing. Vacuum. What? Why is a vacuum cleaner determining our understanding of science? Well, what he ended up having to do was he built something known as a cathode ray tube, which you guys have, or at least in theory, may have seen around your house maybe 15 years ago in our televisions. Our televisions are made up of cathode ray tubes, okay? Old school televisions. We've since advanced. This was a really large cathode ray tube. And what was the goal of this? What was it doing? Well, what he went through and did was had this nice glass compartment. And he had 2 places where we could conduct electricity. And so he would start pumping an electric field in. Okay? If this chamber had something in it, that electric, or the electric charge, as it tries to jump to the other electrode, would impact those particles, nothing happens. No current is translated. Okay, so nothing occurs. But what happens if we remove all of those particles? If instead of there being air in there, we turn it into a vacuum. Now that electric, or the electric charge that comes out of our electrode, jumps out, and it now has nothing to hit. So it's going to go to its counterpoint, which would be the other electrode. As it moves through space, some of those electric particles impact some random floating things in the solution, because it's not a perfect vacuum, and it begins to fluoresce. So we can see this nice kind of pink color show up. The other thing that was kind of neat about it, when those electrons hit the end of the glass started to fluoresce, and we saw these bright colors. Okay? Well, if you put a vacuum on it and you sucked out all of the atoms that are in there, there's now nothing in there. Why would you see any color? You wouldn't. So this is why he was able to establish that we had some smaller particles. How did he determine what was going on with the charge? Well, he saw this and thought it was fun, so he took through something else that has a charge associated with it, also known as poles, like a magnet. You have a north and a south end of a magnet. And what's happening here is we're firing electrons through the air. Electrons have a charge. If we bring that magnet up to it, and it's aligned favorably, the electrons go towards the magnet. And what ends up happening? You see the color start to dissociate or disappear lower. What happens if you flip the magnet around? It goes up. That means whatever was passing through there had to have a charge. That charge was not explained by Dalton's theory. This is why we had to have some additional pieces to it. This is where electrons and protons came from. Okay? So kind of a fun, neat observation on where this was coming from. Okay? This discovery also excited several scientists within the field, and we saw a lot more developments of our atomic theory coming from it. I would argue most importantly is this kind of experiment, this invisible energy floating through the air, okay, is what potentially inspired another famous person that then allowed a lot more discoveries to be involved or created. Guesses what that famous person's name was? I would step away from Rutherford. She is even more important than Rutherford. Curie. Curie saw this and said, hey, this is cool. Let's see if we can find another source of it. Where did she find that other source? Radiation. Okay. Different phenomenon entirely, but it's that invisible energy that they were trying to look for and try and understand something about that kind of pushed that extra research. So it's kind of neat. So Thomson took this and said, okay, atoms now have to be composed of these negative and positive particles. Okay? And he thought back to his experiment with the magnets. We had the north and south end of a magnet, so he said, okay, what we've got are these negatives and positives floating through here. Let's come up with a way that makes the most sense for these particles to be put into our atom. He says, okay, if I take the north end of my magnet and I butt it up against the south end of my magnet, what happens? They attract, and then effectively what happens to the magnetic field in the middle? Disappears, and we end up extending our magnet. What happens if we take the north end and the north end? They repel. So this attractive repulsive force is what he was using to define his theory. We get the attractive force that keeps it as an atom. But we get the repulsive force to prevent any of those things from being immediately next to each other. Okay? Because if we took all of the positives and put them in one spot, we're taking all the north ends of a magnet and jamming them into one spot, what happens? Repulsive. Falls apart. We took all the negative, all our electrons, and jammed it into one spot, what happens? Again, the repulsive force. So he said, okay, you know what? It just has to be kind of this pudding model, this plum pudding model, where he had the plums floating around in the sea of pudding. Okay, so it's not a bad idea. Based on the information that he had to work with, that was pretty solid. Okay, everything seems to match. Okay. One extra thing he was able to do was come up with the mass to charge ratio, but he wasn't able to nail down the mass exactly, okay, or the charge. Another fun experiment to talk about when we're looking at these kind of things, because it gives us something about the mass. Millikan is the one primarily given credit for this, but he had a lot of help from Fletcher and Eyesight and Patience. They took an experiment where they took some oil. Okay? And when you spray oil, you get these kind of little oil droplets misting everywhere, right? Well, oil will carry a charge with it. Okay, so what they did is they sprayed the little oil into this chamber. Okay, and they had to keep the chamber relatively closed so they could trap where those oil droplets went. And what they did is they separated that chamber away from a massive electric field. And there was a tiny little hole between those two. And in that tiny little hole, one of those particles could fall through, maybe a couple. Okay? The reason they wanted to do this hole is that if we just put up a microscope and look at those oil droplets, we're going to see billions of droplets. That's going to be impossible to look at or count or focus on, just a pain. So what they went through and did is made that hole kind of small so you get one droplet. So they can then put the microscope at the end of it and say, oh, I see a little droplet. Kind of cool. Okay? That on its own isn't that big of a deal. What they then went through and did is applied an electric field to that small little section between. That electric field, they can then calibrate to counteract gravity. We're getting that same negative, positive, repulsive force on our charges. Okay, why do that? Because then they can freeze, effectively, the droplet in space. Okay? Then through the microscope, they can predict or measure the size of that droplet. Because it's a sphere, all they need is the radius, and they can now determine the area of that. They know that it's oil, so they could now predict something about its mass. And then they can go through and look at how much charge they put into it. And that charge has to counteract the falling effect of gravity. All of that information put together, they could then predict our masses for the individual particles. Okay, masses, and I'm pretty sure charge, but that's not on there. Okay? An intensely amazing experiment to be able to put that together, and requires more patience than probably anybody here has the patience for nowadays. Okay? Definitely including myself. I wouldn't even attempt to think of doing that. Okay? So it's kind of a neat experiment, and it gets us some information about our charge. Once we had the charge, Thomson could then go back through and figure out our masses, because he had the mass to charge ratio. Once you know the charge, and you know the mass to charge conversion factor, you can then determine the mass. Kind of neat. So we found some more information about these particles. Okay. Rutherford then came along. So here's your Rutherford. And he wanted to come up with some way to either prove or disprove Thomson's theory. Okay. So this is kind of an interesting experiment, okay, as far as the design. So fun stuff we can talk about. What they went through and did is they took an alpha particle source. So some species that fires off alpha particles in a very controlled fashion. We'll get back to the alpha particles in a second. Those alpha particles then go flying out of this instrument and right at a piece of gold foil. Okay? If Thomson's theory was correct, the alpha particle would pass straight through, because there's nothing massive enough within that gold foil or within a gold atom to stop the alpha particle. So what they did is set up a detector on the opposite side of it and just detected, did the particle pass through? Okay? So a couple of things would be that we want to address here first. Number one, alpha particle. What the heck is an alpha particle? Okay? Alpha particles are a form of radiation. Where did he get the source for our alpha particles? Okay? Not an easy thing to get a hold of. This source has to be something very pure and very consistent with its emission. If it's not, then we can't predict when and where our particles are going to come out, and our experiment is useless. We have to control the variable of that source. Okay? So how could he get a hold of that? Well, who was our primary discoverer for radioactivity? Curie. Okay? Curie spent a lot of work going through and isolating radioactive compounds. And in particular, I believe it's radon. Okay? I think it's radon. No, radium. Okay? What's special about radium? It is an alpha emitter. It emits alpha particles. Okay? Why is that important? Well, it needs to be a pure sample. What did Curie go through and do? She designed a protocol to isolate and purify radium. Okay, well, why is that important? Okay, well, that protocol is now her intellectual property. What did she do with that intellectual property? She gave it to the world for free. Why is that important? Now Rutherford can use that information to design his experiment so that he can prove that Thomson was wrong. Without that information, we would have slowed the progress of science. We wouldn't have the understanding that we would now have, because we wouldn't have that radioactive source to begin with. Okay? So that's kind of my plug both for Curie and anti-patents. Okay? Patents destroy science. They do not help it. Okay? Anybody that tells you it helps it is just trying to make money off of it. It's an entirely different issue. Okay? So back to the science of what happened here. So what do we think? Was Rutherford trying to prove Thomson right, or was he trying to prove him wrong? Okay, if he was trying to prove him right, he's saying those alpha particles are going to pass straight on through, which would mean if he's going to set up a detector to detect those alpha particles, where should he put his detector? Just on the other side. Okay? That way, when the particles go flying through, they hit the detector. Oh, of course you were right. Okay, I might be a pessimist, a bit mean here, but what I think is Rutherford said, you're full of crap, I'm going to come up with a better theory. And what his theory was is that there had to be some center nucleus. So instead of just putting the detector at the end, he wrapped that detector all the way around it. So now, when the alpha particles hit, if Thomson was indeed right, they would all just pass straight through, nothing cool. What happens if Thomson was wrong? And we have a densely packed nucleus, or densely packed anything within the atom. Now the alpha particle comes running up, hits it, and is deflected either minorly or all the way backwards. What did you end up seeing? We saw a lot of deflection of those alpha particles. That deflection disproves Thomson's theory, because Thomson's theory doesn't have anything massive enough to stop the alpha particle or to deflect it. So that means we end up shifting to a new theory where we now have a nucleus. And in that nucleus, we now have something densely packed that is going to be the source of all of our protons. All of our protons get jammed into this individual spot. We now have this super dense place where we have our atomic structure. Okay? So kind of a neat experiment and a neat observation. Some other random facts that we can talk about. The atom diameter is 10 to the negative 8 centimeters, and your nucleus is 10 to the minus 13 centimeters. Those are fun numbers considering we're looking at a negative and an exponent. So let's scale that up to something more reasonable. If we made the atom the size of the superdome, the nucleus is a marble sitting within that superdome. Okay? So the size difference between these is astronomically huge. Okay? Your nucleus really is super, super compact. Okay? So we get some interesting things out of this. Rutherford then also predicted that we had to have neutral particles in addition to the protons. What's the evidence that we need neutral particles? Okay? The big one that I would say the textbook puts out there, but not quite as interesting to me, is mass. Could look at the mass difference. We've got the mass of a proton, we got the mass of an electron. We could add up those masses, and they happen to not match our atomic or our atom mass. That means there has to be something else present. It's not contributing to the charge, so it's got to be neutral. Okay, what's our other big reason we have to have something in there? What happens when we take the north end of a magnet near the north end of a magnet? They repel. What happens when we take a positive charge near a positive charge? They repel. How can we possibly fit, say, even something relatively small like helium, two positive charges that close to each other? We can't. Something has to hold them. Okay? So our evidence, in my opinion here, is that we have to have something minimize our repulsive force. Okay? So he's postulated this neutral species in there. And it needs to be neutral because if it was positive, we've only made it more repulsive. If it was negative, why would it be in the nucleus to begin with? We've now annihilated that charge. We don't have that charge in the nucleus. Okay? So kind of interesting observations that we could put to that theory. This was actually experimentally discovered and perhaps named by James Chadwick, and that's where we get neutrons. Neutrons have the exact same mass as a proton, but they have zero charge. Okay? Other things we can evaluate as far as our masses go. You'll notice that the proton is 1 relatively, or that's what our standard is. What is the electron? Okay, 1 over 1,836. So if we're going to look at the mass contribution of electrons to an atom, how much do the electrons contribute? Very, very little. So little that if we want to look at the atomic mass or an atom mass, we don't even count the electrons in that total. Okay? Most circumstances. Okay? Kind of some neat observations. So that takes us down to these three big main categories, our electrons, our protons, and our neutrons. Now what we need to do is understand how we can put them together. Okay? This is where we get atomic notation from. We've already discussed symbols, so we got our symbols in theory now memorized for all of our elements. We're now going to start incorporating some extra numbers. each element has a characteristic number of protons in the nucleus. This is your atomic number. The atomic number in this atomic notation is found in the lower left-hand corner. Sometimes it's referred to as Z, I guess. But I don't really know. Okay? Where can we find that information, say, on the periodic table? Where's the atomic number on our periodic table? Okay. It's in the upper right-hand corner. How do you know it's in the upper right-hand corner? Every periodic table is going to have slightly different formatting. Okay? Just like every map has slightly different formatting. We've got a map of Chandler-Gilbert, and we can see where all the buildings are. If we wanted a map of the city, we probably wouldn't see all the buildings anymore. Why? Because we don't want a map that fills up the entire room. We want something manageable. So to figure that out, we'd have to go to a key or a legend. On our periodic table, every single one should have a legend that explains where your atomic number is, and then our atomic mass, or our mass number, or atomic weight. All of them get a lot of the same numbers, okay, or names. So make sure you're aware of that information on the periodic table. Next part is your mass number. The mass is going to be what makes up the total mass of your atom. Okay, we said the electron was so small that we don't count it, which means we're going to count the protons and the neutrons in our mass. Okay? So our A value is the number of protons plus the number of neutrons found in the upper left-hand corner. Altogether, we now have the atomic notation for an individual element. Okay? So let's go through and manipulate with an example for one of these. Let's take a look at the examples. 2914 Si. What's the element? How do you know it's silicon? It was Si silicon, right? Theory, that's one of the ones you've got memorized. What's your atomic number? 14. Okay, we know it's 14 because it's nice and color-coded, and it's in the lower left-hand corner. Where's the atomic number on the periodic table in our room? In our upper right corner. Okay, so our atomic number is 14. Our mass number? Okay, 29. Where is that found on our periodic table? Okay, according to our little key, it says the atomic weight is found in the bottom left-hand corner. Okay, this is silicon. It says 29. What does the periodic table say? 28. That's interesting. The numbers don't match. It seems a bit odd. We'll come to that in a second here. Okay. There should be an equal sign here. If I want to know the number of neutrons in this element, what do I need to do? 29 plus, whoops, should be 29 equals number of our protons plus the neutrons. Do we know the number of protons? 14 from our atomic number. What can we do? Subtract 14 from both sides, and we now know number of neutrons is 15. Okay? Okay. We will end on this slide, I promise. Periodic table's got a lot of this information up there. We've got our atomic mass, our atomic number, and the symbol. Last thing I want to address is we've got our atomic structure, our electrons, protons, and neutrons. We've talked about the protons and neutrons and what they mean. We've not yet talked about the electrons. Let's go through what the protons and neutrons mean. What does a proton tell you? Positively charged, true, but what does that tell you about the element? If I give you one proton, what element are you? If I give you 2 protons, 3 protons, 6 protons. So as we shift through our table, those atomic numbers go up based on the number of protons. So what do the protons tell us? Protons will define the element. Okay. So if you've got 60 protons, then, oh, that was a bad example, I don't know that one. 76 protons, you've got osmium. Okay, so the number of protons will tell you exactly what that element is. If we change the number of protons, what happened to the element? It also changed. Okay, what do the neutrons tell us? What do neutrons contribute? What was their charge? Big old donut hole. They had no charge, so they can't contribute to the charge. What do they contribute? The mass. Neutrons contribute to our mass. Okay. What I want to go through is change this slightly or a little bit differently. When we looked at silicon, we had 28 versus the 29 that we evaluated. It was still silicon because it had the same number of protons. What changed was the number of neutrons. What's the relationship, or how do we refer to silicon 28 versus silicon 29? They're known as isotopes. Neutrons will define the isotope. The next slide is all about isotopes. Okay? So we'll pick up there on Tuesday. We will finish the rest of this first section of Chapter 4, move into Chapter 5, and then fun of all funs, we'll look at quantum mechanics.